Okay, so it's 12:40. I'll go ahead and just do the introduction now. So let's see here. Okay. Hello, everyone. Thank you for joining us from your homes all around the world to attend DataCon LA 2021. Let's give Eysha Shirrine Powers, Chief Architect from IBM, a big DataCon LA welcome. My name is Aaron, your host, and co-hosting with me today is Chijioki Izumura. We will be moderating the chat and Q&A for everyone that's joining the session. And I would love to give a brief background of Eysha. Eysha designs and develops cryptography software for IBM enterprise systems. Her expertise is in cryptographic key usage and management, data encryption and decryption, signature generation and verification, key algorithms, hash methods, and crypto coprocessor management. Without further ado, I present to you Eysha and her exciting talk on Trust No One. Take it away, Eysha.
Thanks so much, Aaron. And also thanks to CJ for helping to host in the background. So hi, everyone. Welcome to the session. I hope you guys are having a really great conference so far. I definitely miss being there in person, but hopefully we'll get there, maybe next year. We'll see. So as you heard, my name is Eysha Shirrine Powers, and I am a huge crypto nerd. I've been working at IBM for about 17 years now, which is a little crazy. Didn't know I was going to end up working there for like most of my career, but I absolutely love the work that I do. I love working in crypto and security, and I love working on mainframes. So if you haven't seen me present before, that's probably new to you, is that yes, mainframes still exist, and yes, I do work on them actively, and you probably use them every day and don't know about it. If you've ever gone to a bank, you're probably using a mainframe. So it's good for you guys to know. So the backdrop of some of this will be mainframe and thinking about enterprise computing and protecting data. But hopefully this is a really cool session, and you'll learn a lot about fully homomorphic encryption. How does that differ from traditional encryption? And then I'm going to kind of end with a demo showing you the fully homomorphic encryption toolkit, which runs on Linux, and not just Linux on Z on the mainframe, but it runs on Linux even if it was on your x86 box or other systems. And maybe you guys will play around with it, get started with it, and see kind of some of the benefits and value there. Okay, so let's get started. So this is something I'm sure you guys already know, which is that using encryption is really, really helpful for protecting systems, whether you're protecting just your laptop with things like whole disk encryption, or whether you're protecting huge servers and you have your disk encryption and application encryption and network encryption and all of those things. And really from a business perspective, if you're working at a really large company, you're trying to protect your company, you're trying to protect your clients, right? There's going to be, risk and financial loss if there is a data breach, right? You're going to be in the news. Your reputation may not, hold up as well. You're going to have fines that you may have to pay depending on which regulations that you have to comply with. So there's lots and lots of reasons for you to encrypt data besides the fact that you, maybe like me, just think crypto is just really, really, really cool. So hopefully you love crypto and know that it has a lot of benefit to your business and to your organization and to your company or to your personal life. Okay, so let's take a look at traditional encryption. And we're going to look at two different things. We're going to look at the encryption of data in flight. We're going to look at encryption of data at rest. So with traditional encryption, you're thinking about, encrypting data in flight, right? Because you're on the internet, you're on your mobile phone. You need to be able to send across, your password, so you can authenticate to various systems. How do you do that securely? Well, you do that by establishing a secure connection before you actually even send any private or personal or secret data across. And you can do a lot of this is happening behind the scenes, of course, in your browser, right? Where you are, you have that browser. You can kind of see the example here where, you have your browser requesting a secure connection to a server. Server sends back a certificate. The browser validates that certificate, says, yay, that looks good, generates a session key on your behalf, and then encrypts that session key with the server's public key. Sends it back over to the server. The server says, okay, now the server can decrypt that, session key. And now you have a session key which is shared between the two. You can just kind of send data back and forth with that session key. Now, something important to note about network encryption is that data is secure in transit, from that one point to the other point and any other points in between, that data is secure. However, when it comes to your time to use that data, that data is often in the clear. So you have to decrypt the data before you can actually use it. Maybe if you're doing a SQL query, or if you have an application that's processing the data, you have to decrypt it so you can actually do the, whatever operation you want to perform. And so that's one of the things about network encryption, or just about traditional encryption in general. You generally have to decrypt the data in order to use it. Now, that same thing also applies to encryption of data at rest. So let's look at data at rest. So data at rest is really fun too, because you can think of like many different, encryption or cryptography technologies that you can use for data encryption. Oftentimes when we talk about data at rest, we look at it from this pyramid perspective of different layers, of encryption that you can do. And depending on which, depending on what's important to you, what criteria matters to you, you might decide to encrypt at one or more of these layers. So just to break that down a little bit, at the bottom of the pyramid, that's the widest part of the pyramid, you have things like disk level encryption. That's when you think of like that, you think of whole disk encryption. You mean everything on that disk is protected. So 100% protection, which is wonderful. It's usually one of the easiest forms of encryption to turn on. You turn on, everything's protected, and it's yay, it's happy. With full disk level encryption or full disk encryption, essentially it protects someone from being able to, take your disk and try to use it. They can try to take your hard disk and try to make use of it. Or they can try to steal, like if you have like a huge storage device and you have, the different devices plugged in, they might try to steal one or two of those. So full disk encryption protects you from tampering, or protects you from protects you from theft. Now, that's great and all, but, if a person can log onto your system, maybe it's an insider attack, maybe it's someone that hacked in, got through your firewall, then this level encryption is not going to protect you from that type of attack, right? Because once you've, brought your computer system online, now anyone has access to the data in a clear. So from, within that computing system, your data is available. So then you can say, well, okay, disk encryption is great for that one type of attack. Well, you might layer on other types of, encryption or crypto technologies to protect from other types of attacks. So one of those might be something that we call data set level encryption, which is similar to like file level encryption, meaning you're, encrypting like individual files, we call data sets in the system. And what that means is you can actually have more control. So notice that at this part of the pyramid, it's not quite as wide as the disk level, but it's still pretty wide, because when you think about file and data set level encryption, there's going to be some files or data sets that you probably won't be able to encrypt. Things that you're using to boot up your system, those may not be a good idea to encrypt, because you kind of need those in order to boot up your system, in order to get the cryptographic key so you can do the crypto operations to decrypt the file that you needed to boot the system. So there's a little bit of a chicken and egg problem there. So there's going to be some data sets or some files that you encrypt and others that you don't. But it does allow you to encrypt things. So if someone's into your system, you can control who can actually access the file or who can't. Now you go up a level to database encryption, and now we're looking at your database. So this is more narrow because it's only a specific type of application that this applies to, but it gives you an additional level of protection that you may not get with file or disk, right? Because with database level encryption, now you can encrypt data in memory buffers, which means someone who's, if you have a problem with your database, and you're a big company, you have a problem, you're going back to your vendor saying, hey, somebody fix this. They usually are going to tell you, hey, give me a dump of that data. What was the data in there, so we can try to recreate the problem, try to solve the issue. And well, what happens to be in that data? Well, if it's a database of sensitive information, I mean, you're essentially handing over your sensitive information to a third party. May not be so great. And so in that case, if you have database encryption, then your data is encrypted in memories. When you ship that over, give that to that third party, the data is encrypted so they can't see it. So that's really awesome. Now, at the top of the pyramid is application level encryption. And this is the smallest one, not because it only covers a little bit, because it allows you to pretty much encrypt as little or as much as you want to. You get a lot of flexibility there when it comes to encryption. However, it also is the most complicated form of encryption too, where you have to code the application. Now, many of us are developers, we're coders, and so we're not going to shy away from, application level encryption. But it's just important to note that as you go up the pyramid, not only does do you get more complex, but you also get, more security. So it's a trade-off between complexity, security, and also breadth, how much coverage you want. So that's kind of what's represented by this pyramid. But the one thing that still holds true, regardless of what level of the pyramid you're looking at, is that with traditional encryption, the data still has to be decrypted when you want to use it. When you want to use it in your application, when you want to read it in the file, that data has to be decrypted. Always. Any of these methods, your data has to be decrypted. So when you're looking at data privacy and you're trying to protect your data, you're trying to protect yourself, your data, your company from different types of attacks. And we talked about some of those on the previous slide. Now imagine in your environment, you have different roles, different people with different positions, they can do different things. So on the right-hand side, you have Chris, who's your data center technician. And he's just a person who has like physical access to your storage media, to your systems, because he works in the data center, you know. Now, of course, if you're working on the cloud, then of course, maybe some of these names you'll be like, oh, well, there's no data center tech. There probably is a data center tech. You just probably don't know that they're there because to you, everything is in the cloud. But there's a data center somewhere that has your data on it. And there's a data center technician who is managing it, installing the new computers, installing the storage, installing like the different adapters and all that fun stuff. Okay, now you also have Eve here, your storage administrator. That person is the one who's kind of managing the storage, who has access to this storage versus that storage, what level of access do they have. They're the person that knows kind of which applications are associated with which disk or which files or data sets. Then you have your database administrator. That's the person who's managing that database, making sure that all of the queries and all of that is going smoothly. You're going to have your data owner who owns the data. You're going to have your security admin who owns, who's just securing the entire system. And then you're going to have, your LoRa person who's a support person who may get the dump of your data. So considering these different roles that could be in your environment, you're trying to protect your data. The real idea is to have least privilege, and you can start to control these things. You can say, Chris, hey, I'm going to encrypt my data at the disk and tape level, so now Chris has no access to it. So Chris may have physical access, but he can't actually make use of any of the data. He can't view it in the clear. And then let's say you want to layer on top of that data set level encryption. Well, now that you've done data set level encryption, you can make it so even though a storage admin can move data sets around, rename it, and allocate things, they can't actually read or write or open those data sets. So, sorry for Eve. And now think about your support person, right? If you turn on database level encryption, now you're encrypting data in memory buffers. So when you dump those memory buffers to give it to the support person so they can diagnose any problems, and they can't see the encrypted data either, at least not in the clear. And then if you encrypt at the application level, now your database administrator, who normally will be able to see everything coming into and out of that database, now what he gets is essentially just encrypted data, so he can't see anything. So essentially what you're left with and what you're trying to really get down to is the least privileged. Who are the least people that should have access to the data in your environment? In our case here, the data owner and the security admin. Now, what's interesting is you can do this on your system, right? You have full control over your system. You can control and you can set these things up. But what happens when your data leaves your environment? That is the question. So you are the data controller, right? You're the person, you own the data. The data is yours. And what you want to be able to do is you want, to send your data off, maybe to a cloud, maybe to a microservice, some cool application out there is doing some machine learning, it's doing some analysis, it's doing some really cool stuff. And so what you want to do is you want to send your data there to be processed so you can get some value from, that processing that's being done. So you're the controller sending data to a data processor. But when you send that data to that data processor, how do you know if they're going to protect your data as well as you do? So you may have different layers of encryption and different security technologies and different policies and processes that you implement, but you don't know what they have or if they're going to secure the environment as well as you will. Now you can think about the different types of data that you may be sending over there to get analyzed. It could be social security numbers. It can include healthcare information. It can include credit card numbers. So these are sensitive information, things that you would want to be protected and be kept private. And so you always have this kind of in the back of your head, is the data going to be protected? Is there going to be a breach on this other system that I can't control? And then are you at risk? So let's say you are the data processor. So you're the processor, you have received this data from all of these different organizations. They're sending you data because you have this really cool application that's processing it and giving a lot of valuable analysis and information to those different organizations. So you're that processor. Well, can you provide assurance to those organizations that you are unable to access their data, that you're unable to access sensitive data? So you're the one who's receiving these social security numbers, healthcare information, and credit card numbers. What can you do? So question is, well, what if you could unlock the value of your sensitive data while also preserving privacy? Cool idea, right? Like, what if you could make use of, that analysis and those algorithms, machine learning and things like that without having to sacrifice privacy and security? And that's the concept that we're going to try to look at today. We're looking at something called fully homomorphic encryption. So fully homomorphic encryption is not a new topic. It's been around for many, many years, but it's getting more and more attention. It's getting more and more, there's more and more speed. And there's also a whole bunch of new use cases that we're finding to use fully homomorphic encryption. But let me go ahead and kind of explain the idea behind this. So with fully homomorphic encryption, the idea is that you want to keep your sensitive data encrypted at all times. So as I showed you before with traditional encryption, whether it's across the network or data at rest, you encrypt the data, you store it somewhere, move it somewhere, and then when you want to use the data, you have to decrypt it. What if you can encrypt the data and then you can do stuff on the data and that data is encrypted the entire time? The only person that has access to the data in the clear is the data controller, the person who actually owns the data. So let's break down the steps of how this works and what this looks like. So step one, first step, you're the data controller. You're going to encrypt the data, right? This is your sensitive data. It could be financial information. It could be health information. It could be personal information. You're going to encrypt it first. So on your system, you're encrypting that data, unreadable to anyone else. And then you say, hey, I heard about this really cool program out there and it can do analysis of data and it supports fully homomorphic encryption. So you say, awesome. So what you do is you send your encrypted data over to that program. It could be in a cloud, it could be some REST API, some service that you're invoking, but you're not sending it clear data. You're not sending it your keys. You're only sending it the encrypted data. And you're saying, here, process it just as it is encrypted. And because that application supports fully homomorphic encryption, it's going to do its operation. Its machine learning models and everything is all expecting encrypted data, and it can handle that encrypted data. And so it's doing all of its analysis and everything on encrypted data. And when it's done, it's going to send that data back to you. And that data is still encrypted. So it's operating on encrypted data and it's sending you back encrypted data. And guess who's the only person who actually can decrypt the data? It's you. You never gave your key to that organization. So they can say, yeah, they operated on it. The data was encrypted. They didn't have the key. They couldn't see any of the data in the clear. You get the data back, and now you can decrypt it with your key. And now you can actually make use of the results. So essentially what you've done is you've kind of offloaded, send some of your, data over to this environment to have them work on it and get it back, and ensured or assured that essentially that data remained encrypted all the way through. So that's really, really awesome. So let's say and you think of, well, why would you want to send your data off and come back? There's different scenarios. There's a couple of examples that I have here. Financial fraud. There's really cool algorithms to figure out whether or not there's fraud going on. There's cool algorithms around DNA and health. There's a lot of cool things that you can do. If you want to work with third parties and you want to kind of take advantage of different analysis and machine learning. So there's a lot that you can do. And the idea is that you want to be able to do those things without having to compromise security or privacy. So let's take a closer look. So I kind of talked about this, we're the data controller side, but then you also have the data processor side. So on the data controller side, this is where you have your data in plain text. It's in the clear on your system, and you have the fully homomorphic encryption engine. And so since you have that engine running in your environment, you're the person that goes and actually encrypts that data. And then, so your data is encrypted, in your system. And then what you do is you push that data over to the data processor and say, hey, here's some encrypted data. You can kind of see the little ciphertext looking text there. And you push that data over to the data processor. The data processor is going to do computation on that encrypted data. And then it's going to send the results back to you. And then on the data controller side, now you have received this data back, and now you can actually decrypt it and process the results. So at no point in time was the data processor able to see the data in the clear. So this is good for the data controller because you have assurance that your data hasn't been modified or viewed. And even if somebody had gone and there was a breach of the data processor, you're still good because you only sent them encrypted data. And then you, as the data processor, let's say you're on the other side of it, you have assurance, and you can say to your clients, hey, hey, we only got encrypted data from you. We couldn't, that doesn't matter, hopefully they don't have a breach or anything like that either. But even if such things should happen, they don't have to worry about it because, hey, the data was encrypted the entire way through. And they can say to all of those organizations and companies that they're trying to do business with, hey, it's definitely send your data to us, send it fully encrypted, and we can operate on it. We can send it back to you encrypted. And that's kind of a unique value that you may be able to offer to your clients, to say that they don't have to be concerned about the security on your platform or on your systems because the data is always encrypted, even as it's being operated on. So here are some use cases. You've heard me talk about machine learning a lot. That's definitely a big use case. Other use cases will be encrypted search. Of course, I talked about analytics, encrypted AI, biometrics. There's a lot of different use cases that you can use for fully homomorphic encryption. I will say the one use case that you probably won't see on these charts is it's not really like used for transactional type operations. So it's not used like when you're going into your bank account, or you're doing like things that you would normally do, like encryption and transit, or things where you're like, opening a database and you're trying to encrypt the data that's going in and going out as it's going through its transactions. So it's really used for things that are kind of like bigger, like those, machine learning type applications, AI type application, those types of things is what it's used for. Now, eventually, of course, you could get to the point where we can do more transactional things as it gets faster. But there's a lot of really strong use cases, especially for those who are looking at machine learning, AI, analytics, biometrics, a lot of really great use cases to make sure data stays protected, just pretty much even as it leaves your environment. So the question is, who is the intended audience for fully homomorphic encryption? It is data scientists, application developers. I say on here, no cryptography experts, but that's not really true. Crypto experts use too, but the point is that you don't have to be a crypto expert to use fully homomorphic encryption. I'm going to kind of show you a little bit of that, but you do not have to be a crypto expert. I'll repeat it a third time. You don't have to be a crypto expert to use fully homomorphic encryption. Really, the audience for this is you. We want you to use, these tools. The idea is to make it simple enough for application developers, data scientists, anyone to use this very, very easily. And if you have feedback, we would love to hear feedback on your use of fully homomorphic encryption. So what I'm going to do for the next 8 minutes or so is I'm going to take you through a short demo. We'll see if it works. Of course, whenever you do a live demo, you never know how it's going to go. But I would like to kind of show you this toolkit. And there's a link. If it's not in the presentation that you download, because I just added this, I can also send that to you, or maybe I'll paste it in the chat. But if you go out to GitHub, you can look up FHE IBM, and you can get to the information on the FHE toolkit because it's out there. It's available for you guys to use. So I'll just give you a quick demo so you can see it. So let me escape out of here. And this is attempting to reconnect because I had disconnected it earlier. I stopped it because I wanted to be able to start it so you guys can see. So let me show the desktop, clear this away so there's less clutter here. And so I want to do my system here. This is just an Ubuntu system. And in here, I'm going to start the toolkit. So I have a little cheat sheet of commands that I'll use for this system. So let me do that. But just to kind of explain the steps. So at this point in the Linux, so what I have done is I have actually gone out to the page. So I've gone out to not that one, not that one, here's one. So if you go out to GitHub and you go to the Linux, you can go and see the FHE toolkit here. You can see all the different files here. If you scroll down, you'll see more information about the toolkit, and then you'll also get step-by-step instructions on how to run the toolkit. Now, the version that I'm doing now is I'm doing the advanced document, playing around with that. So the step that I actually did before what you're seeing now is I did the git clone. So I cloned the repository, and now I'm in the FHE toolkit Linux folder. I already built the Docker images, and instead of using CentOS here, of course, I use Ubuntu. I can look at the Docker images and see them there. But what I'm going to do now is I'm actually going to do a run. So I'm actually going to do this option, but I'm going to do it with Ubuntu. So let me go ahead and I'm going to run, and we're going to see if it actually will do what I want it to do. So let me go here. Basic development is open for business. So it looks like I am good to go there. So I'm going to go back here where it was kind of spinning for a while. I'm going to reconnect. And yeah, this is not private because this is a self-signed certificate. So that's why you see that. So just an FYI, just for the demo purposes, it's a self-signed certificate, which means the browser is not happy because it can't go to a CA and verify it. Okay, so waiting for some stuff to load here. Okay, there's my prompt. So I'm going to use this build here, and that is for S390 is for the IBM Z mainframe. And so I'm going to use that version for the build. And we're just going to let that run. Okay, so that is good. So now I'm going to go ahead. So now that I've run that, it's pulled in the compiler. Let me do the build. And what is this doing? Essentially like building my workspace and environment and everything. And I'll show you kind of what's included there, what you'll see. And you're going to start to see some of the examples: privacy preserving key value search, credit card fraud detection, inferencing. So in this environment here, it's like essentially an IDE. So you can actually go here. You can see the build and all the CMake. You can also go here, examples, which is really nice. And you can actually see the code for the examples. So here, one of the things we're going to run, we're going to do a search on countries. It's a country lookup. We're essentially doing an encrypted search. So we're going to do that. And you can see some of the code here, which is written in C. You also have, there's another one, work country, packed country database, blah, blah, blah. That's for that. Oh, there we go. Credit card fraud. So there's also the credit card fraud. You can see those details here. So essentially all of this is code that you can go, you can look at, you can run. That's kind of what's meant by this toolkit. It's meant to be something really, hands-on, something you can really see and understand, fully homomorphic encryption. So let's actually do one of the demos because that's always fun to just see it working. So let's do the country one first. So first thing I will do is we built the workspace. I'm going to move this little thing out of the way so I can see. And I want to play. And I want to play privacy preserving key value search. And basically what this is going to do is it's going to ask me, select a country, and it's going to tell me what the capital is of that country. But it's all doing it on encrypted data. So it's not your typical lookup. So if I put in like a country like Germany and I hit enter, what it's going to do is it's going to go through and it's going to look up the capital of Germany. And I can put in other countries as well. Oh, thanks, Aaron, for putting the link out there for me. I just see that now in the chat. So it just found Berlin. I've played around with the different countries. I think I've done like France. Oh, wait, let's see. We did Korea result. I actually may have to play it again and then to France. Okay, there we go. I think I did at some point find like some country that it didn't like have in here, but generally speaking, you get the idea is that it can actually do search on encrypted data as part of the value. Now let me show you the one that I think is really, really cool, which is the example around credit card fraud detection. So let me play that one. And this one does take a little bit of time to run, so I will say that. So it'll run in the background and I'll kind of explain some things that you're seeing. But what you're going to see is you're going to see like a client side and then you're going to see like a server side. And I think it has 24 of these different things that it's going through. And as it goes through those different things, you're going to see that the client side is actually doing the encryption of the data, encrypting the model. And then on the server side, what it's doing is taking that encrypted data and it's processing that encrypted data and trying to detect whether or not there's fraud. And the fraud detection is essentially based on machine learning algorithm that they're using for fraud detection. But the whole point is that it's doing the actual operation itself on encrypted data rather than doing the operation on clear data. And that goes back to like the value of, hey, you want to send your data off to some data processor, some, cool tool out there, and you want to get the value and the results back from that application that's being built. But you don't necessarily want, them to have access to your sensitive data, like credit cards, for example, in case there's a breach or an insider attack. And so what you can do is you just send them the encrypted data. And as long as that data processor supports fully homomorphic encryption, then they can operate on that data without ever having to decrypt it and still send you the results back in an encrypted form so that only the data controller can actually access the data in the clear. So that's really the value here. And so I think if I scroll up far enough, you'll see the different batches. So let's look at batch 24. That was the last one. So here you can see on the client side where it's encrypting the samples. It says plain samples, but that means like plain text or clear samples. It's saving those encrypted samples. It's going to send those over to the server. The server is going to load those encrypted samples, do its prediction, right, using machine learning over those samples, save the encrypted predictions, send that back to the client, or the client can load those predictions, decrypt it, and then assess the results. And then, of course, just like any machine learning algorithm, you can see, the score, the precision, and things like that for the algorithm. But just think this entire, process was done on encrypted data.
Very nice. Thank you so much, Eysha. So we do have 10 minutes left for Q&A. And we do have some questions here. Is that okay? I would hate to interrupt your flow. But...
Oh, no, go ahead. I think the only other thing I was going to mention on here is that there's more information in the deck about blogs and how to join and surveys and stuff like that. But I want everybody to jump in. Yeah, definitely ask questions.
Love it. Awesome. So this is a question from an attendee, Akiva Jesselson. And they say, so this tool is only for developers or data scientists? Is it not targeted to end users like finance or accounting who work on sensitive data?
Oh, absolutely. I think maybe I should have caught that a little bit more. Application developers of all sorts, right? It can be in the finance, it can be, you can build your own homegrown internal. You don't have to be a data scientist. It's any application developer. I should have probably highlighted that more.
No problem. And let's see. So I have a question for you, Eysha. With quantum computers on the rise, and how it's kind of like they're cracking these cryptographic functions, or however you want to call it. How do you see the I think you called it homomorphic encryption? How do you see that in the future against being cracked by quantum computers?
So what's interesting with quantum is quantum can break different types of algorithms depending on the length of the algorithm and what type it is. So right now, the concern in the industry is around the asymmetric algorithm. So think like RSA, elliptic curve, those things that we use for like key distribution and digital signatures are most at risk. Even your RSA 4096, which you think is super strong, yeah, that can be broken really, really easily with a quantum computer. Elliptic curves is better. Of course, but RSA, yeah, that's going to be out of there. But you don't worry about that today, fortunately, because we don't have enough qubits yet to actually break it. But the idea is as they increase and have more and more qubits, then those asymmetric algorithms are at risk. Now, for the symmetric algorithms, those have less risk. So essentially, their key strength or cryptographic strength is kind of cut in half. When you think of quantum. So you still are okay if you're using like AES 256 and those for like traditional encryption. Now for fully homomorphic encryption, the algorithms that they're using are actually lattice-based. So they're using lattice-based cryptography, which is quantum resistant or quantum safe. So for fully homomorphic encryption, it's not, at least at this point, it's not a concern because the algorithms that they're working with are quantum safe algorithms.
Oh, thank you so much. And we have another question. So from Chijioki, he's asking, would it determine when the encryption keys are compromised without any imminent attack yet? And yeah, I'll let you answer that.
So would it determine if the cryptographic keys, so I'm gonna ask you to repeat that again.
I was kind of iffy about it, but I thought, oh, Chijioki, go ahead.
Eysha, man, thank you so much for the presentation. I mean, I don't know so much about security, but I was just asking, would it be able to determine when the encryption keys are compromised without any imminent attack yet? Right.
Yeah, I think so. That's actually one of the big challenges that I see just in crypto in general, whether you're using fully homomorphic or using other encryption, is how do you know when the keys have been compromised? Generally, you may not know a key has been compromised until you see your data on the dark web somewhere, right? And that's when you know your cryptographic key has been compromised. However, you can add layers and layers of security to prevent the key from being hard, or to make it hard, really, really hard. Because your goal really as a security person, right, is to make it as hard as possible for someone to, breach your system. You want to make them go through like as much work as you could think of. Think of a labyrinth. You want them jumping through hoops. You don't want it to be easy. Your goal is to make it as difficult as possible. So you can do layers of things like making sure that for your cryptographic keys, some keys you can store them in different key parts, and you can have different key owners for those different parts. So that can help you against like things like phishing, whether it's targeted phishing or not. You can think of things like having like strong cryptographic keys. I think for fully homomorphic encryption, they're already pretty strong keys. So there would be, you will have the risk of a brute force attack if you use really short keys, right? So I will say that it's very difficult to know if a key has been compromised unless you have seen that, unless you're kind of like post-breaching, you're like, oh, this is what happened. There are some signs to know that you are at risk of a compromised key, which would be if your key was stored somewhere in the clear, if you only have one key custodian, if you have maybe a disgruntled employee, somebody's really, really, really bad, really unhappy, then you may be at risk. So those kind of scenarios. But from my perspective and what I've seen in my years is it's really tough to know when a key has been compromised. So what we do is we just try to protect against it and to make it as difficult as possible to, get those keys.
So let's see here. Oh, thank you for your response, by the way. So Akiva is following up with their question from earlier, and they just want to get some clarification. So this, the intended audience would more or less be for developers and not necessarily for technical users. Is this right?
I think that everybody should know about the concept of fully homomorphic encryption, because I think even if you're not a developer, just knowing that it exists, then you can work with your development team to implement it. I don't know if there are any box solutions for homomorphic. Actually, there may be some. I know IBM services does tend to make services available around homomorphic encryption, so they might have some out-of-the-box solutions that don't require development. For this particular toolkit, you definitely have to be a developer. But what I can do is I can look up and see if there's some out-of-the-box solutions around fully homomorphic encryption. I believe there may be some that are available now that would not involve coding, but will allow you to make use of it. So I will have to investigate. So you may have to send me an email. I have my email address. If I scroll back far enough. On the first slide here, eysha@us.ibm.com. So if you can email me, then I can go and look and see if there's anything out of the box that doesn't involve having to code.
Very cool. Thank you so much. So we currently, I think that exhausted the amount of questions we have for right now. Any other insight you would like to add, Eysha?
Just that I hope people like this session, and that it's a really cool technology. I remember when I first heard about it, maybe like a few years back, I was like, oh, this is awesome. And then I would hear articles and they would say, oh, well, it's too slow for this, it's too slow for that. And I'm like, oh, it's kind of a bummer. So it's great to see that now we have these really cool use cases, and that also the performance is sped up so that we can use it for some really cool stuff, because AI, machine learning, analytics, that's all like here. It's now, and everybody's using it. And so it's great that we have like these really strong use cases for homomorphic encryption where we can protect data and also be able to do these new and cool, or use these new and cool technologies.
Yeah, it is really cool, and I think you're on the forefront of all of that, and I think IBM's doing a great job in kind of trailblazing these different technologies.
Yeah, it's very cool.
Let me see. Let me ask the audience. So would anybody have any other questions at this time before we conclude this presentation? Let me see. So it looks like okay, if there's no other questions, I would just like to add some concluding remarks, if Eysha would like to do so before me.
So I just would like to thank everyone for attending this session, for hopefully go out there, play with the toolkit, look at the slides. There's a bunch of links in there to tell you what you can do with homomorphic encryption. Just have fun.
Excellent. Thank you so much. And really, thank you again, Eysha, for being here and for presenting this amazing topic. And I think there's a lot of value to be gained from your insight And the demo was pretty cool, very complex to say the least, but it is very cool. And thank you again for all the attendees for your questions and your interactions during the session. I would implore the audience to contact the speaker if there's any questions specific to this topic. And to us at DataCon LA, feel free to provide your feedback, any comments you may have. And thank you again for joining today's presentation. Have a wonderful day, and thank you for being a part of this year's DataCon LA. Bye.